Hello, welcome to the third online lecture for rational choice theory. In this lecture, I wanted to go over a proof that we went over in class, but we didn't have a time to go over all of the details of the proof. So just to remind you, this is a proof about when a choice function is rationalizable. So the set P of x here is the set of all non-empty subsets of the set X. So X, as a reminder, is the set of all options that the decision maker is faced with. So the set of all non-empty subsets of that will be sometimes called menus. So a menu, these are the choices placed in front of the agent. Now a choice function is any function that maps a menu, so a non-empty subset of X, to the set of choice-worthy options in that menu. Okay, so C is just going to be a function from P of X to P of X such that for each menu, C of A picks out the subset of A, the options in A that are considered choice-worthy. Now a derived choice function is any choice functions that's derived from the agent's preference relation or preference ordering, strict preference ordering over X. So we derive this preference ordering as follows. We let the choice-worthy options in a menu A be all those options Y such that for all the other options, all the other available options, none of those other available options is strictly preferred to Y. So Y maximizes the preference ordering of the agent inside of A. So that's a derived choice function. And we say that a choice function, just any choice function, is rationalizable if there is a preference relation such that the behavior that we observe, so the choice function C, can be understood as a derived choice function, where the derived choice function is defined in this way right here. All right, so the theorem that we're interested in is this theorem, that C satisfies the weak axiom of revealed preference if and only if C is rationalizable. So to prove that, this requires two parts. We want to show that if C satisfies the weak axiom of revealed preference, then C is rationalizable. And secondly, so that's the first part of the proof. The second part of the proof is that if C is rationalizable, then C satisfies the weak axiom of revealed preference. So we're going to first prove the second one here, that if C is rationalizable, then C satisfies the weak axiom of revealed preference. So if C is rationalizable, then we know that C is equal to a derived choice function where this greater than sign is a preference ordering. So if that's the case, in order to prove that if C is rationalizable, then C satisfies the weak axiom of revealed preference, in order to prove that statement, we simply need to show that this preference relating, the derived preference relation, satisfies the weak axiom of revealed preference. So this is what we'll do on this slide here. So here's to remind you, if C is rationalizable, this is what it means. Then C is equal to this derived preference relation, choice function, and this is the weak axiom of revealed preference. Okay, so our claim is simply that this derived choice function satisfies the weak axiom of revealed preference. To prove that, well, we just need to verify that this weak axiom of revealed preference holds for this choice function. So let x and y be elements of A intersection in B. Suppose x is among the best elements in A, and y is among the best elements in B. So what we need to show, so the question is, so we must show that x is actually among the best elements in B. So this is what we need to show, that X is among the best elements in B. So how do you prove that X is among the choice-worthy objects in a derived choice function? Well, what we have to show is that X is not dominated by any element in B. So let Z be an element of B, and we want to show that Z is not strictly preferred to X. So we want to show that Z satisfies the fact that it's not strictly preferred to X. So a picture might help here. So we have two menus, A and B, an option X and an option Y, and now we have this other option Z. Now Z comes from the menu B, and I don't know whether or not Z comes from this part of B or this part of B. So Z could either come from A, so it could be the part of B that intersects A, so it would come somewhere in here, or Z could come somewhere over there. Now, if Z is actually in A intersection B, then what do we have? Well, we have Z is in A intersection B, and X is also has been revealed to be among the best options in A. So Z in particular is in A, and X is among the best options in A. That means X has to maximize the preference relation. So this tells me that Z cannot be strictly preferred to X. So this is, if Z comes from this part right here, from this intersection, then we know that Z cannot be strictly preferred to X. But Z might actually come from the part of B that does not intersect A. So it might come from this part over here. So if Z comes from that part over there, so if Z is not in A, then what do we have? I should just say then. Well, what do we know? We know a couple things. We know that X, well, let's do this one first. Y has been revealed to be among the best options in B. So Y is a choice-worthy option in B. And since Z is an element of B, we know that, I'll say, since Z is not strictly preferred to Y, so Z can't be strictly preferred to Y, because if Z was strictly preferred to Y, then Y would not be able to be among the best elements in B, but it is. We're assuming that. Second thing we know is that X is among the best elements in A. So X is among the best elements in A, and we see here that Y is an element of A. Now, since Y is an element of A, we know that it cannot be the case that Y is strictly preferred to X, because if Y was strictly preferred to X, then X would not be able to be among the best elements of A. All right, then by negative transitivity, we have Z is not strictly preferred to X. So we have Z is not strictly preferred to Y, and Y is not strictly preferred to X. So therefore, by negative transitivity, we get Z is not strictly preferred to X. But that tells me that X must be among the best options in B. So that's the proof. We've shown that C satisfies the weak axiom of revealed preference. All right, now we need to show the other direction. So we want to show that, so we showed that if C is rationalizable, then it satisfies the weak axiom of revealed preference. Now we want to show that if C satisfies the weak axiom of revealed preference, then C is rationalizable. So how do you prove that a choice function is rationalizable? Well, you need to find a preference relation. So a strict preference relation such that the choices you observe is actually equal to the derived choice function of that preference relation. So we talked a lot about this in class, so I'll just go ahead and tell you exactly what this preference, or remind you what this preference relation is. So we define a preference relation given our choice function c, we say that x is strictly preferred to y if and only if, well, when the agent is faced with a choice between x and y, then the only choice-worthy option is x. So this is where the term revealed preference theory comes from, because the agent is faced with a menu, a choice between x and y, and what the agent reveals is that the only choice-worthy option is x. So we have to show two things. One, we have to show that this derived relation here is a preference relation. And two, we have to show for all menus A, the choices that we actually observe are in fact the derived choices that you would get if the agent started with this preference relation. So we have to show these two facts. All right, let's go ahead and do that. So this is just to remind you of the definition of our preference relation. And now, instead of using the weak axiom of revealed preference, it turns out to be more convenient to just work directly with Sen's alpha and beta conditions, which we talked about those before. So now let's prove, so our claim, let's prove, which I think was the second statement, that for all A, so for all menus A, C of A, the choices we observe are actually equal to the derived choices that we would get if we used this preference relation. All right, so we're showing that two sets are equal. So in order to do that, we have to show first that the choices you get, so this set here, the set of options here, is actually a subset of this set of options. That's the first thing we have to show. And the second thing we have to show is the reverse direction, that this subset, so the set of choices you get in the derived relation, is just a subset of C of A. All right, so we'll first do this. So to show one set is a subset of another set, let X be an element of the first set, so C of A. And now we want to show that X is actually an element of this set right here. So again, how do you show that X is an element of that set? Well, what you have to show is that there is no other option in A that is strictly preferred to X. So let Z be an element of A. So let Z be an arbitrary element of A. We claim, so my claim is that, I'll just write it this way, that Z is not strictly preferred to X. And if this claim turns out to be true, then we see that X has to be among the best objects in here, in the choice, among the best options in A according to this preference relation. Well, suppose it was the case. So suppose Z is strictly preferred to X. Then, well, by definition, so we look back up here, by definition, when the agent is faced with two options, Z and X, what he would choose, or the only choice where the option is Z. So now let's just take stock what we have. We have the small menu consisting of just Z and X. Now since X is assumed to be an element of C of A, we know that X is also an element of A. So what we have here is a menu Z and X, which is a subset of A, and we have both Z and X are in this smaller set right here. So look at Sen's alpha condition, where you let B be this set Zx and let A be the set A. If Z, so then we know that if X is in C of A, that tells me that X has to be in, so by alpha, since X is in C of A, we have X is in C of Z x in the smaller menu. So this is just a direct application of alpha. But that's a contradiction because we were supposing that z is strictly preferred to x. So this leads us to a contradiction. So this tells us that z cannot be strictly preferred to x, like we supposed here. Since z cannot be strictly preferred to x, that means that x is among the best options in A according to the preference relation. So x is an element of this set right here. Okay, now for this other direction, we're actually going to prove it by contraposition. So suppose x is not an element of C of A. Now, if x is not an element of C of A, we want to show that x is not an element of this derived set right here. Now, the way the argument goes, since C is a choice function, we know that C of A is not empty. So let Z be an element of C of A. So we have this option Z here, which we know has to exist because C of A is not empty, and we know it's not equal to X because we're supposing X is not an element of C of A. So our claim is that Z is in fact strictly preferred to X. And if we can prove that Z is strictly preferred to X, then, sorry, this should be X is not there. X cannot be in this set right here in the derived choice function from our preference relation because we found an option which is strictly preferred to X. Okay, so our claim is that Z is strictly preferred to X. Now this is going to follow relatively straightforward. So consider C of Z X. All right, so the agent is faced with two options, Z and X, and our claim is so we want to show that this is actually equal to Z. Because if that's the case, then Z will be strictly preferred to X. Now, one thing we know, this might go a little bit quick, but notice that Zx, so again, we have Zx is a subset of A, right? And let's suppose that this is not the case, that C of Zx is not equal to Z. Okay, so we want to suppose that this is not the case. So let's say suppose this is not the case. C of Zx is not equal to Z. Well, that would tell me that X has to be an element of C of Zx. Now, if X is an element of this set, since C of Zx is a subset of A, what we have is by the beta condition here, so here we have to let B equals A and A equals Zx. By the beta condition, we are going to get, since X is an element here, so X has been revealed to be at least as good as Z, and Z has already been revealed to be among the best options in A, that tells me that X must be among the best options in A. But again, that's a contradiction because we were started off by supposing that X is not an element of C of A. So it's not among the choice-worthy options in A. Okay, so this shows that for all menu options A, the derived choice function matches the choices that we observe. Now all we have left to show is that our derived choice function is a preference relation. Okay, so how do you show it's a preference relation? Well, you need to show two things. One, you have to show that, so our proof, so we have to show first that this satisfies anti-symmetry. So this is asymmetric. Well, this follows just straightforwardly from this definition right here, because suppose that X is strictly preferred to Y, then when faced with the menu between X and Y, the only choice-worthy option is X. But that tells me, just by this right here, that it's not the case that when you're faced with a menu between X and Y, that the only choice worthy option is Y, but that is enough to say that Y is not strictly preferred to X. So asymmetry follows just by the definition. It just falls out of the definition. Negative transitivity is a little bit more complicated. So we want to show that, so our claim is that this is negatively transitive. Okay, so suppose, we need a proof, suppose X is not strictly preferred to Y, and Y is not strictly preferred to Z. But X is strictly preferred to Z. So this would contradict negative transitivity. So I'm going to derive a contradiction. So if X is strictly preferred to Z, that tells me that when faced with a menu between X and Z, the only choice-worthy option is X. And now I'm going to run, the argument's going to run as follows. I'm going to ask myself, consider the menu consisting of X, Y, and Z. Now I know this has to be non-empty, so the choice here has to be non-empty. But I'm going to show that none of X, Y, or Z can be an element of can be a choice-worthy option, can be an element of this set. All right, so this assumption right here by Sen's alpha condition, so let A here, so let in the alpha condition, let A be the set X, Y, Z, and B be the set X, Z. So X, Z is a subset of X, Y, Z. X, if Z was an element of the larger set, so if Z was an element of the larger set, then Z would have to be an element of what must be a choice-worthy option in the smaller set. So if Z is chosen when faced with a menu between X, Y, and Z by Sen's alpha, then Z must be chosen when faced with a menu between X and Z. Okay, so Z cannot be an element of this larger set because we know that X is the only element in C of X, Z. So we get that Z is not an element of this larger set. Well, now we know, suppose that Y is not strictly preferred to Z. So if Y is not strictly preferred to Z, this tells me that when faced with a menu between Y and Z, this is not equal to singleton Y. So Y is not the only element in the choice set here. So that tells me that Z has to be an element of C of Y, Z. Now, if Y is an element of C of X, Y, Z, by the alpha condition, since the set YZ is a subset of X, Y, Z, we have that Y must be, so this is by the alpha condition, Y must be an element of C of YZ as well. But if that's the case, then we have Y and Z are both in this smaller set YZ, so they're in this set A. YZ is a subset of the larger set XYZ, which is a subset of B. I've supposed that Y is an element of this larger set. So this then tells me that by the beta condition, that Z is an element of C of X, Y, Z. Now, that we already just showed up here. So earlier we just showed that Z cannot be an element of C of X, Y, and Z. So where we're at right now, I need to erase a little bit. So I'll just go ahead and erase some of this. Where we're at right now is that I've been able to show, So this is where we're at right now. I've been able to show that z is not an element of C of x, y, z, and y cannot be an element of C of x, y, z. Now, since choice functions are non-empty, this tells me that x has to be an element of this set. Right here. But we'll see that that leads to a contradiction for the exact same reason why y was not allowed to be in there. Because remember, we also assumed that x is not strictly preferred to y. So that means that C of xy is not equal to singleton x. So the choice you make is x is not the only choice-worthy option there. So that tells me, of course, that y has to be an element of C of x, y. And again, you do the exact same reasoning. If x is an element of the choices you make in this larger set, then by the alpha condition, x must be a choice in the smaller set. But that'll tell me then by the beta condition, because we've assumed or we know that y is there, that y actually must be an element of this larger set. X, y, and z, the choices that you make when choosing among the menu x, y, and z. And that again is a contradiction. So in all cases, this leads to a contradiction, and the assumption that led us to this contradiction is that x was strictly preferred to z. That's what led us to all of these contradictions. So therefore, all of this implies that x is not strictly preferred to z, and that's what we wanted to show. So this completes the proof. I wanted to go through the details, sort of explain the details. We touched on this in class, but this is the whole proof together in one place.